Hello everyone. We want to continue on the subject of resistivity. So we defined a couple of parameters and I'm gonna review those parameters first. So the first parameter that we discussed and the first concept was the resistivity. So in terms of resistivity, we had a couple of definitions. We had the resistivity of water or brine basically, and resistivity of brine is equal to the resistance of brine multiplied by cross-sectional area divided by length of your sample. And the way we found the resistivities or of the brine was through using the available charts that we had. So one of these charts that is basically a Schlumberger chart relates the resistivity of brine to the temperature and the amount of salt that is dissolved inside your water. So on the right hand side of the y-axis you can see the part per million, which is the amount of salt that is dissolved inside our water. On the x-axis you see two axes here. One is basically in the temperature in the Fahrenheit. This is the temperature in centigrade, and the y-axis on the right hand side, on the left hand side of this chart, is giving you the resistivity in ohm meter. That's the unit of resistivity. So you basically need to have the amount of salt that is dissolved. You need to have the temperature. So if you have the temperature, you go up until you hit the right part per million salts dissolved inside your water, and then you go to the left, you read the value. That's your resistivity of the water. The other parameter that we discussed was RO. So RO was resistivity of a rock 100% saturated with water. So it's equal to resistance of the rock 100% saturated with water multiplied by cross-sectional area divided by length. And the ratio of these two parameters was called formation resistivity factor. We defined it in this slide. So it's RO over RW. And this is called formation resistivity factor. It's an important parameter, and the value of formation resistivity factor is always greater than 1. The reason is that the formation resistivity factor is the ratio of the resistivity of a rock 100% saturated with water divided by the brine resistivity. Now, the resistivity of a rock 100% saturated with water is always higher than the resistivity of the brine itself, because the rock have matrix, and matrix basically, or the grains of the rock, have the infinite resistivity. So the resistivity of this RO is higher than the RW, so this ratio is always greater than 1. So we want to see what factors would change this formation resistivity factor. Many factors play a role. Of course, the water, which is basically inside the pores of your rock, the salinity of that water would change your formation resistivity factor. The temperature would change basically your RW and RO, and therefore it changes your formation resistivity factor. The rock porosity, water saturation, what type of clays you have. Clay is a conductive material as opposed to the other type of rocks. Clay have multi-layers of ions and cations that can transfer and can transmit electrical current through it. So the amount of clay, the distribution of the clay inside your rock would change the resistivity of your rock, and therefore it will change your formation resistivity factor. If you have fractures, of course, if you have basically some other type of conductive minerals inside your rock, then it will change your formation resistivity factor. Now, let's look at some of these parameters. The first one we want to look at is the porosity. So consider that you have a porous media which is made of bundle of tubes. This model, we have discussed it in previous chapter. Very simple model for porous media. So consider that you have a rock, a cubic shape, and there are multiple tubes in it instead of your pores, and everywhere else the porosity is 0. So if you look at the cross-sectional area of this rock, which is basically the total cross-sectional area, which is this part, this is AN, and sorry, this is the A total, which is the total porosity of the total cross-sectional area of your rock. So this is A, and each of these nanotubes or tubes basically have a cross-sectional area AN, and then you have N number of these tubes within your rock. So you can say that your area for each of these tubes is porosity multiplied by cross-sectional area. So that relationship exists, and the resistivity of your water is, again, that's the definition we discussed it, voltage divided by current multiplied by the cross-sectional area of these tubes, because the water exists, or the brine exists inside these tubes, and the length of the core sample, in this case this is your length, and that's the definition of resistivity. So formation resistivity factor is defined as RO over RW, and if you put the relationship considering the same voltage and same current passing through the pores and the rock, then formation resistivity factor is basically equal to 1 over porosity. This is 1 over porosity, right? So porosity and formation resistivity factor are have a reciprocal or a type of relationship. Another important factor, we consider these rocks, these pores to be straight, right? So what if you have a flow path that is not straight? So look at this figure. You have basically this LA is the length of your flow path, and L is the total length of your rock. So we define the tortuosity of porous media to be equal to the length of the flow path divided by the total length of the rock squared. That's the definition of tortuosity. Now if we put tortuosity into our equations, now look at what have been changed. The resistivity of your rock 100% saturated with water is still the same relationship. This length here is the length of your porous media or rock. Now the definition of RW, however, is different. The length of the flow path is important here, and this is the length of your pore. Length of, I should say, flow path. This length is the total length of rock sample. And now if you divide these two by each other to get the formation resistivity factor, you will have this LA over L appear on your equation, and that's the definition of this LA over L is square root of tortuosity. So formation resistivity factor is equal to square root of tortuosity divided by porosity. You should be careful, this equation is very simple, right? We didn't consider very complex nature of the pores, so this equation really cannot be applied. So people have tried to derive experimental equations, and the general format of this equation have been proposed by many researchers. One of these equations is Archie equation. So this Archie equation, you can see it here at the bottom. He did some experimental measurements and relate the formation resistivity factor to porosity, and he found that there is another factor here, which is, you can see it's M. It's called cementation factor. And basically what it tells you, the cementation factor, is how good the grains of your rock are cemented together. Okay, so he proposed this relationship. Some other researchers have tried to derive equations and find correlations that relates the porosity to formation resistivity factor. One of these famous equations is Humble equation. So these equations, these two equations are Humble equations. Depending on what type of rock you're using, you basically could use any of these equations. So he put a factor of 0.62 divided by porosity divided by 2.15, or 0.18 divided by porosity squared. So these are formation resistivity factors. And FR, generally, if you write a general equation, can be written as A over porosity to the power of exponent, the cementation factor. So this is a very general relationship. How can you use this equation? Possibly, if you have the data of formation resistivity factor, you can design experiments to saturate your rock sample 100% with brine. And if you have multiple rock samples with different porosities, and you measure, so let's say you have sample number 1, sample number 2, 3, 4, and 5 samples, and these 5 samples have different porosities. So 5.1, 5.2, 5.3, 5.4, 5.5. These are different porosities of different samples. And what you do is to measure the RO for each of these experimentally. So you have RO1, RO2, RO3, RO4, RO5, and let's assume that you use the same brine, so your RW stays constant. So if you do this experimental measurement, then you will find different values of formation resistivity factor for each of these samples. So you will have basically F1, F2, F3, F4, F5. And once you have these data, then if you look at this equation, let me create a new slide. And all right, so let me write here. So I just mentioned that you have number of samples, right? For each of these samples, you have different porosities: 5.1, 5.2, 5.3, 5.4, 5.5, and then each of these will have different values of resistivity: RO1, RO2, 3, RO4, RO5. And then you can calculate F for each of these samples by dividing RO by RW. Let's assume that you use the same brine for all these samples. So you can calculate F1, F2, F3, F4, and then F5, right? So what you can do in order to find the constants of this FR equation, A over phi to the power of M, is to write the equation. So F is equal to A over phi to the power of M, and take a log of each side. Then it's going to be log of A to the phi to the power of M, then log of F is equal to, use the log rules, so that would be log A minus M to the M multiplied by log of porosity, right? So if you plot log of F that you have found as a function of logarithm of porosity, then you will find an equation, couple of data points, right? And then feed a line to this equation. The slope of this line is going to be M, the cementation factor, right? And then you can use any of data points to find A, or basically the intercept of this. Here is log of A, right? So you can use this to find the cementation factor and constant A. So in next video I'm gonna do an example.